So in the previous video I showed you a graph like this that I drew by hand, which shows the size of the universe over time. And we saw how there was a couple different options like this recollapse where it expands and contracts back and crunches again, or kind of a slowing expansion that reaches some maximum size, a constant expansion, or, which was the surprise, this sort of accelerated expansion. And what I want to illustrate for you is that these four possible fates of the universe can be expressed and distinguished by two of these cosmological parameters. And I explained before how one of them was the mass density of the universe, how much stuff is in the universe, omega m. Well, that made sense, right? Because if there's more stuff in the universe, it's more likely to collapse again under its own gravity. But this other constant, the cosmological constant, okay, we call like omega nu, I guess sometimes, but usually people just call it the cosmological constant. And you can see that for all of these cases where the universe is either slowing or going at a constant rate, we'd say that cosmological constant is 0. But in the case of an accelerated expansion, we'd say that cosmological constant is 0.7. Right? So this is a way, a mathematical way of expressing the accelerated expansion of the universe. Now, astronomers collect data, right? And they can distinguish between these different models. Basically, by looking at galaxies and other events far away, they can look at things that have a really large distance between us and them, and we're also looking back in time, right? Because the further back out into space we look, the further back in time we're looking, because the light takes so long to get to us. So these are all data points helping us kind of distinguish which of these is most likely. As you can see, this idea of a recollapsing universe is pretty much completely ruled out. There's really no data to support that. But the data is kind of overlapping between sort of the coasting and accelerating case. But you can see that it seems pretty overwhelming that the majority of the data is falling on top of this accelerating case. Right? But the more accurate the data that astronomers get, right, the better we can understand these sort of things about our universe, like what's going to happen 10, 20 billion years in the future of our universe, and what happened 10, 20 billion years ago. Another way of presenting this is probably a little confusing, but I just want to show it to you anyways because it's kind of cool. This is a graph that astronomers often use, and this is a graph, this is advanced, okay? They call this a graph of parameter space. So this is a graph of what the mass density of the universe could be, right, between 0 and 3, the omega m, how much stuff there is in the universe, and what the cosmological constant could be. And you'll see this shows a couple crazy things. One is these colorful regions show different sources of data, different types of data, ways of collecting data, like using the cosmic microwave background, or using supernovas, or using clusters of galaxies, right? All sort of independent ways of trying to measure these parameters. You'll also notice there's this line here which says expands forever or eventually recollapses. And here's, oh, and even another line here, like a flat universe versus an open universe versus a closed, right? That has to do with the curvature, right? Closed would be like curved, positively curved, like the surface of a ball. So there's all these different things that are shown on this graph. What's interesting to see is where all these different sources of measurements overlap each other. So like the supernova remnant, or the supernova data, says these parameters must be somewhere inside this oval, right? And the cosmic microwave background says somewhere inside this oval. The cluster says somewhere inside this oval. And where they overlap kind of in this region means that's pretty close to the actual measured values. So what is that? It's a mass density of about 0.3 or 0.4. And it looks like a cosmological constant of about 0.75. Now we saw that before as one of our options here, right? That's the curve that's shown in red, 0.3 and 0.7. That seems to be what the data is telling us. All right, now what's crazy about this is that acceleration means there has to be some value for this cosmological constant, which means there has to be some sort of dark energy. Now there's a crazy story behind all of this. And well, I should just say, okay, astronomers don't know what the mechanism of dark energy is, okay? But what's amazing is that it was actually sort of predicted in a certain way by Albert Einstein. And I think Einstein gets probably too much credit, okay? So he was really smart and everything. It's pretty amazing, but it's not like he well, he didn't really understand what his equations were even predicting. So you probably know that this idea of relativity is tied to Einstein, and a part of that is general relativity, which is how gravity works, and the idea that space is curved by mass. So that's how gravity works. Well, when Einstein came up with his equations, and I just want to show you what the general equation of general relativity looks like, and I've never taken a graduate school course on general relativity, so I don't even really understand how this equation works. I just think it's cool that there's an 8 pi in it. But this equation, when Einstein developed this equation, came up with it, he noticed that it predicted, and this is in the 1920s, it predicted that the universe must be expanding. And at that time, nobody knew yet that the universe was expanding, right? Like Hubble had not yet discovered that. But Einstein, just like sitting at a desk with a piece of paper, predicted, based on his equations, that the universe must be expanding. But because nobody knew that it should happen at the time, he added what he called a cosmological constant to eliminate, in the math, just to eliminate the expansion of the universe. Because everyone thought the universe was not expanding. He called it the greatest blunder of his life because he had the opportunity to predict the expansion of the universe before it was discovered, which would have been unbelievable. But what's fascinating is that, in effect, Einstein was putting in a negative dark energy. Like he was trying to remove the expansion of the universe with the math. You know what I'm saying? But what's crazy is that this idea of a cosmological constant has come back, except it's not slowing the expansion of the universe or eliminating the expansion of the universe. It's accelerating the expansion of the universe, which not even Einstein's equations of general relativity predicted. Craziness. All right, so it's pretty cool. But you can see that this amazing data that we've collected gives us this really awesome perspective now on both the history of our whole universe, but also the future of our universe, which is super cool.